Good morning all. This is our second section of our module 6, that is power system stability. So we have seen what is the power system stability is the property of a system under normal operating conditions to remain in a stable operating equilibrium or to regain to its original state of equilibrium even after the occurrence of a disturbance. Okay, and we have classified the power system stability into three main categories depending upon what are the parameters we have discussed. Depending upon the nature of the variable we are classifying, depending upon the size of the disturbances and the method of the prediction and calculation, depending upon the time duration that is happening and depending upon the control procedures and processes, which we have classified our power system stability into three categories. That was a voltage stability, a frequency stability, and a rotor angle stability. Okay, and we also discussed what is the need of doing this type of stability studies. So from this we understood that these stability studies gives us vital information about the highest magnitude of power system parameters that can have. Okay, so it gives us the vital information, and these informations can be used for designing all our protective systems and our process systems, and it also helps us to calculate the maximum power transfer capability, and hence it also helps in the future planning, that is generation. Is there any generating unit to be installed, or is there any compensating network required in that system? So these all things can be get from our power system stability studies. Okay, and then we have went to our types of power system stability. Okay, in the first thing we came to know was we have to study on the voltage stability, that is to maintain a steady voltage, or to maintain we have to keep the generation and load balance. Okay, and we have seen that what are the disturbances that occurring in the voltage stability, or what are the causes of instability was the sudden change of the load, or tripping of the transmission line, or malfunctioning of the protective systems, or these all things will relate to the will lead to the cascading of the fault, or sometimes voltage drop at the transmission lines, increase and decrease of the self-excitation systems in the generating units, or the capacitive charges in the transmission line. All these can cause to the voltage instability. Okay, so depending upon the nature of this voltage stability or voltage, depending upon the nature of this problem, what we have done is we have classified our thing in voltage stability into small disturbance and large disturbance voltage stability. Small disturbance means it requires only a small load change. Small disturbances will happen in small disturbance voltage stability, that is usually the load change. Okay, for this we need only linearized differential equation to analysis, and the main factors which help in damping of the this voltage instability problem, or that helps to control, are the characteristics of the load in which the system contains, and the control actions and the protection systems we employ. Whereas in a large disturbance voltage stability, the cause is a large disturbance. Sometimes it can be a fault or a contingency, and for this we need for the damping of this also we have to take care of the load characteristics, and for the analysis we have to deal with the non-linear dynamic system. Okay, and whether they can be brought back to our normal stable state or normal operating condition, that depends upon the nature of the load and the level, the process control level they have employed, and also the protection scheme they have employed. So this deals with the voltage stability, that is the voltage should be maintained constant. Okay, and next comes to the frequency stability, and since the name itself it denotes the frequency stability, is that we have to keep our frequency a constant. That is, last class I said it can be from plus or minus 3%, but it is not like that. We should keep it, the range is correct, we should keep it from 49.5 to 50.5, that is plus or minus 1% alone is only applicable for the frequency stability. So this is also kept constant by the generation and load balance that we will discuss in our this class itself. Okay, and so what are the causes of this frequency variation is the change in the power flow. Okay, this change in the power flow, maloperation of the relays, that is sometimes the under frequency relays operates and load shedding will happen. The generation control, load voltage regulators maloperate, or the prime mover energy supply systems may cause the frequency to change. So these are the causes of the frequency stability systems, and depending upon the time duration in which the fault or in which the instability is sustaining, we are classifying it into the short-term frequency stability and long-term frequency stability. Okay, so what is short-term frequency stability means? It is for a very short seconds. In some seconds only it will sustain, and it will be due to the insufficient under frequency load shedding, and it will lead to under generated islanding, okay, which can in turn lead to the blackout. Whereas long-term frequency stability is little more complex to study, and it deals with the overspeed control of the steam turbines or the protection controls of the boiler reactors, etc. These are little complex and will sustain for several seconds. Okay, so this is so the frequency instability, we are classifying it into short-term frequency stability and long-term frequency stability. And the last classification is a rotor angle stability. Okay, so what is rotor angle stability means? In all the systems, all the generators should work in synchronism or remain in synchronism. That is, in synchronism means they have to rotate at the synchronous speed. Okay, so if they have to rotate at a synchronous speed or a constant speed, there should not be any acceleration or any deceleration. Okay, so there should be a balance between the mechanical torque and the electromagnetic torque produced. Okay, so the mechanical torque should be equal to the electromagnetic torque in order to avoid the oscillations and to keep the rotor angle constant. Okay, so this is the rotor angle stability, that is all the machine should remain in synchronism, and with that it should be rotating at the synchronous speed. Okay, so what is the causes of this instability? Naturally it will be the acceleration or deceleration of the rotor, or the angular separation increases. What will happen if the angular separation increases? The power transfer capability reduces, which in turn make the system unstable or unstable. Okay, and next, what are the types of the stability? That is, usually we will tell it as a small signal stability and a transient stability, whereas small signal stability or steady state stability or a static stability, all these things deals with the small disturbances, that is small change in rotor angle or some oscillations. Okay, so what will happen? It will have an effect, that is a local effect will be there and global effect will be there. In local effect, in some plants there will be the plant will be in an oscillatory mode, or in globally what will happen, inter area mode oscillations will happen. That is the effect of small signal stability. Okay, this stability we can recover without any aid of any automatic controllers, whereas if the same small signal problems or small steady state problems occurs in a periodic time and we are using the aid of some controllers, then we can call it as a dynamic signal stability. Okay, dynamic stability. That means the disturbance is still small, but it is occurring in a periodic time, and we use some automatic controllers to control. Okay, so this small signal stability or steady state, this can also be considered as a steady state stability. Okay, so these two can be studied with the help of our swing equation, which we will be discussing in our next lecture. Okay, and the other part is the transient stability problem. That is, it happens due to the severe disturbance, like what we have discussed here also. No, this is a large disturbance. Similarly, this is also depending on the large disturbance. Okay, so here it will be a non-linear power angle relation, and the limit will be, when compared to the steady state limit, the transient state limit will be very less. And this transient stability, we are studying it with the use of equal area criteria. So this will also be discussed in our fourth part. Okay, this will be discussed, swing equation and all those will be in the third part. and equal area criterion we will discuss in the following part. So these are the brief classifications of our power system stability. I hope you will understand this. This is very important. That's why I am summarizing it again and again. This has been asked for previous university question paper. Okay. The previous questions include differentiate between the transient and steady state stability. That is, transient means large disturbance stability problem. Steady state means small disturbance stability problem. And they have asked more define stability. What are the different types of power system stability? Then what is a power system stability? And questions were asked for, these all questions were asked for 2 to 4 marks. And they have already asked for an essay question, that is find the steady state stability. That problem we will do in this lecture. Then what define the terms. Essay question was asked on May 16th, 2016 May, that is define the term steady state stability, transient stability, steady state stability limit, transient stability limit, etc. And in November 15, the exam before that, it was already asked to explain transient and steady state stability and discuss the methods to improve transient stability. All those questions were asked again and again. Distinguish between steady state, transient and dynamic stability. Derive power angle equation, like that the questions were asked. So I again summarize this, and you have to consider this portion as extremely important portion. Okay, so next what I am going to deal with is I have to go to our power angle equation, which is asked in an essay question. Okay, so in order to derive power angle equation, what we have to study is we have to study a synchronous machine connected to an infinite bus. Okay, so we have to study a synchronous machine connected to infinite bus. Okay, I will discuss the machine as infinite bus. Okay, I will discuss the machine as a generator, and I will just show it as a motor also, and we will derive the power angle equation. Okay, so I am considering a system, that is my generator that is G. It is connected through a transmission line. Transmission line equivalent parameter what we are representing is using my reactance, isn't it, X, and this is generator, no? So the angle is E angle delta. This voltage angle is delta, and generator I am using E angle delta. From this generator, the current will flow through an infinite bus bar. So infinite bus bar I am using the voltage here is V angle 0 degree, infinite bus bar reference. Okay, so this is V angle 0 degree, that too in per unit value. So this is a diagram of a synchronous generator connected to an infinite bus bar. Okay, so we have to derive the power angle equation, that is just the power derived is equal to, we have already studied in our synchronous machines, that it is EV sin delta by X. Okay, or we can write it as P is equal to P max. Okay, from the equation that we will derive. Okay, from the equation what I am going to study is we have to derive the power delivered or electrical power. So that electrical power I am reminding you that electrical power can be equal to P into, that is V per unit into I per unit into cos theta or cos phi. Okay, so that is equal to V per unit into I per unit into cos theta if it is written in the per unit value, or if we are writing in the phase value, then 3-phase power, 3-phase generator, the power will be 3 into V phase into I phase into cos theta. Or if I am writing it in the line value, that is 3-phase value, then it will be root 3 VL IL cos theta. So these are the different equations for our active power transfer. Okay, so next what I am going to do is, why I said this is a very important portion, and usually many questions were asked from this portion for our GATE exams and as well as for engineering service examination. So this portion is little important. So just I have written this equation. If we were given in our question with V per unit and I per unit cos theta, then we can directly directly find out this, or phase value, then we have to multiply with the 3, or then in line value they have given, then we can use the same equation. I just want to tell you this, okay, even if the system is a single phase or 3 phase or anything, we can get our total power, we can get our active power per unit by multiplying V per unit into I per unit into cos theta. Okay, no need to consider whether it is a line value or a phase value. Okay, so these are the power equation. Okay, next what we have to study a synchronous machine connected to an infinite bus. Okay, now my machine is a generator, and this we are getting infinite bus bar. No, so infinite bus bar means I am taking this as my reference because it is V angle 0 degree. Okay, so what it is, I am drawing a phasor diagram, that is, this is my V angle 0. Okay, so this is my reference, and what happens, V angle 0, and so sorry, this is reactance. No, this is my current I. So if I am drawing this current, because reactance, it is inductive, so the current lag and the current will be I phasor. Okay, so this is V and I, and the angle between this V and I, we call it as theta, no, because we are using cos theta. So this is theta, and this voltage plus the potential drop across this will give E angle delta, isn't it? So we are going to find out this voltage E angle delta. So this is current, no, so this voltage V plus I have to add potential across this. Potential across this means potential across this portion means that is I into Jx, isn't it? So J into I into Jx. So this is purely inductive circuit. So the voltage will be 90 degree leading. So this is the current direction, isn't it? So the voltage will be 90 degree leading. So like this. So I am drawing parallel to this as my Ix value. I hope you understood. We have already drawn things like this already. Okay, so this this is the current, and the voltage drop across the pure inductor will be 90 degree leading. Okay, voltage will be leading. So I have drawn this. So this will be parallel. Voltage only alone can add, no? So I am adding this. So we got V into Ix, and this resultant is our E value, and this angle is my delta. Okay, now what we have to find out is, we have to find out the power transfer. Okay, we have to find out the power transfer. What is, I am starting from my apparent power. That apparent power will be equal to P minus JQ. We have started in our load flow analysis like this, no? Or I can write it as V conjugate into I. Okay, V conjugate into I. But this V conjugate, no, that V is its reference angle is 0. So V conjugate, the magnitude will be V alone. So next I have to find out the current I. So how will I find out the current I? So for that, what I will do is, this is 90 degree, no? So if I bring this back and I am drawing this, so this will also be 90 degrees, isn't it? So this will be 90 degree, and also this, if I am drawing straight like this, this can also be 90 degree, isn't it? So this is also 90 degree. So what I am going to do is, I have to find out this Ix first. First I will find out Ix. Okay, magnitude of Ix, and from that I am going to find out I. So what is Ix? Ix is the hypotenuse here. So this portion I am calling it as A, and this is B, I am calling it as. Okay, so this Ix is the root of A square plus B square. I hope you understood. Ix I can say, or Ix is equal to this is the real part, and if this is the imaginary part, I can say my phasor I is a phasor. I into X is equal to, what I can say, that is equal to A plus JB. I can write it in this form, A plus JB. Okay, what is this A? This A, I can say A is equal to, what is, this is delta, no? So this is V, and if I am taking V cos delta. Then what will be this? Here it will come up to E, no? So, sorry. What we have to do is, this is delta, then this is the adjacent side. So if I am taking cos delta, then this value, when it comes to here, it will be, shall I give a number here? So A 0 x y I am giving. Okay, so I am drawing it. So what I have to find out is, I have to find out A, that is equal to OX. Okay, so OX is equal to, if it is some small letter x y I have put, no? So if it is Z, then I should say OX is equal to ZX minus OA, isn't it? So what is ZX? ZX is this E when come to this portion, that is E into cos delta. So ZX is E into cos delta. Okay, minus what is OA? OA is ZX minus, sorry, O, it is not OA, it is OZ, isn't it? So what is it? OZ value is minus V, isn't it? This value. So I want to take this segment, that is equal to this entire line segment XZ or ZX minus this ZO, okay, or OZ. So my OX value, I got it as E cos delta minus V. I hope you understood it. Next segment, what I have to find out is B, that B is XY. Okay, so B is XY. How can I find this XY? That is, this is the opposite side, isn't it? So I can write it as E sin delta, isn't it? Sin delta is opposite by hypotenuse. So I want this opposite side. Opposite side is equal to E into sin delta. So B value I can write it as E into sin delta. So if I am writing in this form, then I can write I into X is equal to E cos delta minus V. All these are magnitude, you have to plus J into, there is a reason I am keeping it as still as J, because I have started from writing my apparent power. Okay, we need only the real power transfer. I am considering the real power only. For that, for real power, we have to take the real part of the apparent power equation, isn't it? That's why I am writing it in the same form. So this is, sorry, here one J is there, J into Jx. This is her potential, no? So if I am writing the voltage, then it should be I into Jx. So I am writing J also. Here what I have to find out is, I have to find out the current value, isn't it? This phasor value I have to find out, the magnitude of the current, or I have to find out the current value. So that for finding out current value, I am using 1 by Jx into bracket E cos delta minus V plus J E sin delta. Okay, so this is the equation. If I am doing this for the current, I am substituting the same to find out my real power or electrical power. That is equal to the real part of this, my apparent power. So if I am taking the real part of the apparent power, then that is equal to V conjugate into I. Since V conjugate, V is V angle 0, V conjugate also will be equal to V value. The magnitude will be same. So V into this I value. What is this I value? That is E cos delta minus V plus J E sin delta by this Jx is there, isn't it? So we have to take the real value only. So I am taking real value only. What is real value? That will be, this V will be there. Then real value, this is an real value divided by this imaginary 1 by J, it will be minus J. So this will be the imaginary part. Whereas we are considering the second term, this J and this J will cancel and the real term will be sin delta by X. Okay, so that's why we are getting power equation PE is equal to V into receiving end voltage into sending end voltage divided by X into sine delta. This is the power angle equation. In our case, what we are doing is we are usually keeping this is a reference value, this is constant. We are generating constant voltage. This will also be constant. This V value will be constant, E value will be constant, and the reactance will also be constant. So these three values will be constant. Then I can say if these values are constant, and so I can write it as a constant, that P max into sine delta. From this equation we can say our active power is directly related to the angle sine delta if the other three parameters are constant. Okay, so if I am drawing a graph corresponding to the same, then how can I draw a graph corresponding to the same? So if I am drawing a graph, so this is my angle delta, this is PE, and delta, sine 0 is equal to 0, sine 90 is again 1, then it will, in 180 it will again reach to 0, isn't it? So the graph will be something like this. Okay, and here the maximum it will happen at value pi by 2 or 90. Okay, so sine 90 the value is 1, then we can say P is at the maximum power, that is P max. That P max value I am taking it as, this is my P max value. Okay, so this is P max, this is delta 0, and this is the power curve PE or electrical power, and this is the angle delta. What is that angle? We can say it as a rotor angle, or we can call the delta as a rotor angle or a node angle, voltage angle, or these are the different names of delta. Okay, torque angle also you can say sometimes. Okay, so this is P max, and pi by 2 it will be maximum, so we notate it as P max. This is the power curve and delta. This relation we call it as power angle relation, and this curve is the power angle curve. This was asked in a university question last year. Okay, so this is power angle curve. So I hope you understood how we got the equation, that is PE is equal to EV sine delta. Power angle curve you understood, which was a university question. Next, I hope you also want to know what is the effect of this machine, synchronous machine, as a motor. Okay, so here I want to add that if we are increasing the delta, then what is delta? Do you know what is delta? That delta is the angle relationship. Do I have to teach you again on delta? If I am having a this machine as a generator, if I am taking this, so I am drawing a rotor. This is my rotor, and this my rotor, and this is my axis of rotation, that is omega r, rotor axis of rotation. So what I am keeping a stationary rotating axis. No, this is my rotating reference axis, that is omega s, and the difference between this omega s and omega r we notate it as delta. That is the difference between the omega s. What is omega s? Omega s is the rotating reference axis of that particular synchronous machine. So omega s is the rotating reference axis, and this is the present axis of rotation. That is the angle difference between the rotor and the reference, rotating reference. We call it as delta. Okay, so that's why I told you, when delta increases, the relative position of the rotor with reference to the reference will be increasing. Okay, so if delta increases, the position between them is increasing. So we can go up to 90 degree and we will get P max. Okay, if the load is constant, and we are changing the excitation. Okay, I am writing the equation again. PE is equal to V into E by X, isn't it? Into sine delta. This entire term we call it as P max. Okay, if these are constant, the real power flow will depend upon the angle only, load angle or rotor angle only. Okay, this is rotor angle. Okay, so it depends on the rotor angle only. Okay, so from that we can say it will increase up to maximum at 90 degree, and then it will decrease, or we can say this is the stable region. This will be the stable region and this will be the unstable region. For example, if some fault occurs in this region, if some fault occurs in the same curve I am drawing, if some fault occurs, if it was working at an angle delta 0, this was my PE 0, and if some fault occurs, then it will move, then it will go and it will become stable if the fault value is within this P max value, or if the delta value increases beyond that, the system will be unstable. We have to prove this only with the help of swing equation. From after studying swing equation, I will come to the multi-machine system which is operating in coherent, that is in all delta constant, and in different delta, that is coherent and non-coherent situation. At that time I will tell you why I am saying this. If the delta value is less than 90 degree, then the system is stable, and if it is greater than 90 degree, the system is unstable. This is also an important question for our GATE examination and PSC examinations. So this is how the power angle relation of a generator. And very slightly I am going to discuss what happens. The machine is connected as a motor. When the machine is connected as a motor, same infinite bus bar I am using, that is V angle 0. Then if I am using it as a motor, then naturally the current flow will be in the opposite direction, X. Okay, so if it is a motor, then the angle will be E minus delta, isn't it? So while drawing our curve, this is my reference V, and the current flow. What will happen to the current flow? The current flow, I have to draw the current. The system is lagging itself. So this is my current. And what will happen? This voltage minus this will give the voltage here, isn't it? Minus, so it should be minus Jx. Okay, so this is I into Jx will be this side. If it is minus, then it will come like this only, in the opposite direction, because it is the cos. Okay, minus J into Ix, it will come like this, and the resultant angle is the value of E, or the motor voltage across the motor, and this angle is my delta. I hope you understood. And this angle, the angle between V and I, it is theta itself. Okay, so here it comes a relation. Hope you remember that relation. We used to say, that is while we are using it as a generator, theta is equal to omega st plus delta. Here it will be this theta is equal to omega st plus delta, this delta, and omega st plus delta. And whereas here in the motor we are taking it as omega st minus delta. We are taking minus delta, that we will discuss again in our inertia constant. We have to discuss on the inertia constant and swing equation. In that lecture I will again tell you how it is. So this is the phasor diagram when the machine is working as a motor. Okay, so when the machine is working as a motor, what will happen? The equation reverses, that is I have to write minus J into Ix is equal to the same V cos delta, V minus E cos delta. This is this voltage. Here we have to find out this equation, this right angle triangle we have to solve. So we have to find out minus, before it was J into Ix, now it becomes minus J into Ix, and from minus J into Ix, then we have to say this voltage, if I am doing this, then V minus E cos delta and plus then this is E sin delta itself. So if I am writing, okay, I'll write the equation. Current equation will be equal to V minus E cos delta plus J into E sin delta, and I have to divide it with Jx because it was Ijx, no? So divided by Jx. If I am taking my real part, so real part alone we need. So this 1 by j is minus j. This j and j it will cancel. So if I am taking real part, V conjugate, the magnitude remains same into I. So the real part of I it will be E sin delta by x. So it remains same. The equation remains same. That is, active power transfer is equal to sending end voltage into receiving end voltage divided by the reactance into the angle sin delta. This relation of electrical power transfer, we call it as power angle equation. Okay, so this we call it as the power angle equation, and the curve we draw is known as, this curve we draw, it is known as a power angle curve. Okay, we are studying our stability with reference to this power angle curve. I hope you understood today's lecture, and we will discuss the problem later on. Okay, thank you.